Let's do the problems from the conditional probability section, starting with the first one. It says, we are drawing a single card from a standard 52 card deck. Find the probability of getting a heart given that it's red. Alright. Now this is the notation for conditional probability. Whenever you see this vertical bar, that vertical bar is red given. So the given or assumed information is always after the vertical bar. So this is how you read it. What is the probability of getting a heart given that the card is red? And there is a formula for this, which says that this is equal to the probability that it's a heart and red at the same time, divided by the probability that it's red. So there is a formula for that. You should know that formula. So keep in mind that there are 52 cards in the deck. If we want to calculate the probability that it's a heart and red at the same time, just count the number of cards that are hearts and reds at the same time and divide by 52. Well, notice that a heart is already red, and I know that there are 13 hearts in the deck out of 52. So the probability of the numerator is 13 out of 52. And notice that half the deck is red, because the diamonds and the hearts are red, 2 out of the 4 suits. So 26 out of 52 cards are red cards. And you can cancel out those 52s on the bottom. You end up with 13 out of 26, which is 1 over 2. So the answer is 1/2. That is the way you do it if you want to use the formula. But there is another way to do it, which is this. What's the probability that the card is a heart given that it's red? Well, half of the red cards are hearts because the other half are diamonds. So you could probably just reason it out without the formula sometimes. It depends on the problem. Number 2. Now, in number 2, it says, what is the probability that you get a heart given that it's yellow? And this is a different problem. We're not talking about cards here. Let me give you the picture. Now, we're given 10 different symbols. This is a smiley face, that's a heart, and that's a star. And I'm letting P represent pink, B represent blue, and Y represent yellow. So every one of these circles has a symbol and a color. So when it says, what is the probability that we get a heart given that it's yellow? Well, you kind of think of the given part as the sample space and ignore everything else. So just focus on the yellows. Let me put a little check next to all the yellows. There's a yellow, there's a yellow, and there's a yellow. And there's one over there too. So it looks like there are a total of 5 yellows. Out of all the yellows, how many of them are hearts? Well, let's see. 1, 2. And actually, I think I just see 4 yellows. But out of the 4 yellows, how many of them are hearts? It looks like just 2 of them. So 2/4 is the probability, which is 1/2. All right. So on that one, I think it's better probably to not use a formula. Whatever the given is, that's your sample space. And in this case, the sample space has 4 symbols because there are 4 yellows. But what's the probability that it's a heart given that it's yellow? Well, 2 out of the 4 yellows are hearts. So 2/4 is the answer. All right. Well, let's do the next one, which is really number 11 in the book. What's the probability that it's yellow given that it's a heart? So they're kind of switching them around on us. Okay. Well, let's go back to the picture. This refers to the same diagram. Well, notice in this case, the sample space consists of all the hearts. So I'm going to put a little X next to all the hearts. There's one. There's another. There's another. And I guess that's it. I only see 3 hearts there. So it looks like the size of the sample space is 3 because there are 3 hearts. Now, how many of them are yellow? Well, it looks like 2 out of the 3 are yellow because this one is yellow, this one is yellow, that one is blue. So there are only 3 hearts, but it looks like 2 out of the 3 are yellow. So the probability that it's yellow, given that it's a heart, is 2/3. Let's do number 4. Actually, I want to skip number 4. Let's do number 5, which is number 43 in the book. All right. Now, this one has a table in it, And I went ahead and sketched the table for you. And let me read the instructions. According to U.S. government statistics, mononucleosis is 4 times more common among college students than the rest of the population. Blood tests for the disease are not 100% accurate. Assume that the following table of data was obtained regarding students who come to your school's health center complaining of tiredness, a sore throat, and slight fever. Use these data to answer the following questions. And in this problem, let's see what the question is. It says, if a student is selected from this group, what is the probability that the test is positive given that the student has mono? So on this problem, we're looking for the probability that the test is positive given that the student has mono. So sometimes you have to kind of translate the words into your own mathematical symbols. All right? But I'm going to show you a nice little trick for answering these kind of conditional probability problems without using a formula if you're given a table. Okay. So once again, we're looking for the probability that they test positive given that they have mono. So once again, the given is kind of like the sample space. So if you're given a table like this, only focus on the row or the column that corresponds to the sample space. In this case, the given is that the student has mono. So given that they have mono, that means we're only going to focus on the first column and nothing else. The sample space actually has 80 students in it, in the restricted sample space. So what is the probability that they test positive given that they have mono? Well, notice that 72 out of 80 tested positive that had mono. So that's the probability. We just have to plug that into a calculator. So the main idea is the given part is the restricted sample space. Well, let me plug that into a calculator. I get 0.9. So that basically means if you have mono, there's a 90% chance that you're going to test positive, which kind of makes sense. It'd be nicer if the tests were a little bit better or more accurate. Well, let's move on to the next one. Number 6. All right, now number 6 also refers to a table. So let me take out the table for you and I'll read the instructions. It says, the Political Action Club has surveyed 240 students on your campus regarding the relationship between their political affiliation and their preference in the 2016 presidential election. The results are given in the following table. If a student is selected at random, find the probability the student is a Democrat given that they preferred Trump. So we're looking for the probability that they're a Democrat, and let's make up our own notation, given that they preferred Trump. And with that event, we'll let it be represented by a T. Okay. So once again, the given is the part that we want to focus on. And the given is that the person preferred Trump. So which row or column do we want to focus on only? It looks like this one, because these are all the students that preferred Trump. And it says, what is the probability that they were a Democrat given that they're only in this second row? So it looks like the answer is 15 out of 98. Because of all the students that preferred Trump, 15 of them were Democrats. So 15 out of 98 is the answer. Let's plug that into a calculator. About 0.153. I'm not sure if they want you to enter this as a fraction or a decimal on your homework. You'll just have to pay attention to the instructions. Let's move on to the next one, which is number 7. which is really 23 in the book. It says, assume that you are drawing 2 balls without replacement from the urn. I think I'm going to skip that one because that one's too hard for me to sketch. Let's move on to the next one. This one actually refers to the table we just did. It says, what is the probability the student preferred Trump given that they were a Republican? Okay, so again, translated into math. What is the probability they preferred Trump given that they were a Republican? So let's go back to that table. And once again, the given part is the only row or column that you want to focus on. So in this case, the given is that they were a Republican. So we'll circle that. Given that they were a Republican, what is the probability they preferred Trump? 68 out of 80. So you can use a conditional probability rule, but in the case of the tables, I think it's better if you don't. I think it's better if you do it the way I just showed you. 0.85. Let's do another one. All right. Now, I'm going to skip number 9 because that has kind of a complicated graph in the book that I don't want to have to resketch. But let's do number 10, the very last one. I think you can probably handle the 2 that I skipped if I do the other 8. This one is number 39 in the book. It says, an experiment and 2 events are given. Determine if the events are independent or dependent. 2 dice, 1 red and 1 green, are rolled. The total is greater than 9 is one event, and the total is even is the other event. All right. So let me summarize. And I'm going to go ahead and make up some notation for the 2 events, because we're going to have to talk about the definition of independent events here. Well, one of them says the total is greater than 9. How about if we let capital N represent that event? And the other one says the total is even. Let's let capital E represent that event. Okay. Now let me just review the definition of independent events. And this should be in the PowerPoint slides too, but I think this will help you. N and E are independent if the probability of N given E is the same thing as the probability of N. That's one form of the definition. All right. By the way, you could also define it like this. The probability of E given N is the same thing as the probability of E. So you can kind of switch them around, but I don't want to confuse you. Well, let's just think about this for a second. This basically says the probability that N happens given that E happens is exactly the same thing as the probability of N. And that kind of suggests that it doesn't matter whether E happens or not. The probability of N is the same either way. That's why they call those independent events. All right. So let's start with the easy one. Let's find the probability of N. So if these 2 things are the same, then they are independent. If they're different, then they are dependent. But what is the probability that the total is greater than 9? Okay, well, let's see. If we're trying to calculate the probability that the sum is greater than 9, well, greater than 9 means it has to be 10, 11, or 12. All right? So let's count the number of ways for the sum to be 10. Well, it could be 4, 6. Could be 5, 5. It could be 6, 4. And I think that's it. How many ways can it be 11? It could be 5, 6, or it could be 6, 5. How many ways could the sum be 12? Only 6, 6. And remember, there are 36 total outcomes when you roll 2 dice. All right? And we use a slot diagram for that because you have die 1 and die 2. Each one has 6 faces, so there are 36 total outcomes. So you don't have to list them all, but it looks like 6 out of 36 is the probability that it's greater than 9. Because we have 6 outcomes out of a total of 36 in the sample space. That's 1/6. Now here's the hard one. What's the probability that's greater than 9 given that it's even? And I would probably use the probability rule in this case. That's the probability of N and E divided by the probability of E. So if you ever forget, the one that comes after the vertical bar is always the one that goes on the bottom. And that's because you kind of think of E as the sample space. Well, let's see. If it's greater than 9 and even, well, if it's greater than 9, it's got to be one of these three numbers, right? But if it's also even, it can only be 10 or 12. So how many outcomes correspond to greater than 9 and even at the same time? 1, 2, 3, 4. Out of 36. Now, what is the probability that it's even? Well, I believe half the time it's even, 18 out of 36. If we really want to do it the right way, we would do it like this. And this is probably good practice for us anyway. But if I want to calculate the probability that the sum is even, well, it's possible for it to be 2, 4, 6, 8, 10, or 12. And I'm going to show you that there are 18 outcomes that correspond to this event. 2 is easy. 4 could be 1, 3, 2, 2, or 3, 1. 6 could be 1, 5, 2, 4, 3, 3, or 4, 2. 8 could be 2, 6, 3, 5, 4, 4, 5, 3. I think that's it. Oh, and 6, 2. And then 10. Well, that could be 4, 6, could be 5, 5, or it could be 6, 4. And 12 can only be 6, 6. So I'm guessing there's 18 of them there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Did I miss one? Let me see. I think I missed one up here. This could also be 5, 1. So there are 18 of them total. So that's really the right way to do it. And once again, you can cancel out those 36s. So this reduces to 4 over 18, and that is 2/9. So here's the idea. Are these two probabilities the same? No. One of them is 1/6. The other one is 2/9. So those are not independent. That means they are dependent. So quite a lot of calculations on that one just to give a one-word answer. But those are dependent.